section, we're going to be talking about statistical models. So in the medical literature, most analyses are conducted using statistical models. Here we're going to cover ones that are frequently used, and we're also going to describe how to interpret the results from them. So in the types of scientific questions section, we discussed what's known as a descriptive analysis. And here, we're not actually interested in fitting a model, but just reporting summary measures. So pulling up that table 1 from the closed trial that we looked into, this is an example of descriptive statistics. So here, the statistical question was just a descriptive analysis. There was no model fit, just point estimates and standard deviations for each of the variables that were measured. But in these other 4 categories, exploratory, inferential, predictive, and causal, we often are interested in fitting some kind of statistical model. And so we're going to focus just on these 3. We'll talk about predictive models a little bit at the end, and then we have a whole section that dives into those. But for now, let's focus on exploratory, inferential, and causal models. So the statistical techniques that we've discussed so far are univariable. And by that I mean they are just looking at how some outcome is affected by a single exposure, or more generally, how some independent variable X is related to some dependent variable Y. So univariable, that refers to that there's just one variable on the right side of that equation. So only one explanatory variable there. So for example, coming back to our difference in means section where we were looking at the difference in heights in that measures of association section, there we were interested in the relationship between group, whether or not you were in the blue or green group, and height. And so that was a univariable relationship. Height was the dependent variable, group was the independent variable. We were just looking at one exposure and how it was related to our dependent variable height. Here's another example that we've been looking at, the comparative analysis of alcohol control policies in 30 countries. So the association of interest here is the alcohol policy score and liters of ethanol consumed per person per year in each of those countries. And this is one of these scatter plots where we just are looking at 2 variables, score and liters of ethanol. So this is, again, the univariable relationship. We've just got the one dependent variable, the liters of ethanol per person per year, and the one independent variable, alcohol policy score. Okay, here's a new example. Here we're interested in the relationship between a person's shoe size and how many books they've read this year. So on the x-axis, or that vertical axis, or rather the horizontal axis, I've got shoe size. On the y-axis, or the vertical axis, I've got the number of books read. And here, again, we're looking at a univariable relationship. We're looking at the number of books read and how that's related to the individual's shoe size. So coming back to that plot, from what we learned in the statistical graphics section on scatter plots, it looks like there's a positive relationship here between shoe size and book reading. So it looks like as your shoe size gets larger, you read more books. But can that really be true? Can we really believe that people with larger shoe sizes really read more? So this is a case where a multivariable model could come in handy. Recall in that data collection section when we talked about confounders. So a confounder, again, it's a variable that's associated with both an exposure and an outcome, or both an independent variable and a dependent variable. And so coming back to this scatter plot of shoe size and books read, it turns out that there's a third variable present, and that's the age of the participant. So here I've highlighted in orange the participants that were children. So some of them have very small shoe sizes and read 0 books because they can't even read yet. And others with very few books were just learning to read. And so this relationship is really largely based on this third variable, whether or not the individual was a child. And since we didn't account for this important confounder, we made an erroneous interpretation of the data. So this is where a multivariable model could have helped us. So a multivariable model, or a multivariable analysis, is one that measures the impact of an exposure on an outcome while adjusting for potential confounders. Or kind of in more statistical terms, it's going to look at the impact of an independent variable X on a dependent variable y, controlling for potential confounders. And so this is going to let you quantify the effect of x on y, holding all these other variables constant. And so back to that example of shoe size, we can hold the age of the participants constant and see if we saw an effect, and we no longer would. So when thinking about potential confounders and whether they should be adjusted for, the study design becomes really important. Randomized control trials naturally account for confounding because the treatment assignment is random. It's assigned via this random process. So there shouldn't be a third variable out there influencing the treatment assignment. And so that's not to say that multivariable models do not exist in randomized setting. In fact, they can make a lot of sense to adjust for things in this case, but we're no longer worried about confounding in the same way. But in observational studies, there is a potential for confounding because now the treatment assignment is no longer random. For example, one study that I worked on, we were looking at 2 different diabetes drugs and their association with heart disease. And instead of conducting a randomized trial, we looked at electronic health record data to see which treatment patients were given, and then we examined their subsequent heart disease. And it turned out that one of the drugs was actually more likely to be prescribed to sicker patients. And so if we hadn't accounted for this, we would end up with a biased result. It could look like that drug led to more heart disease, when in reality, this may have been totally driven by the patient's pre-treatment characteristics or the fact that they were sicker before they even received the drug. So a multivariable model is one way to adjust for this kind of confounding. There are other ways to account for confounding. A really common one is stratifying the regression model. And so now the exposure-outcome relationship is quantified within each stratum. So in the medical literature, it's very common to see models that are stratified by males and females. And this is likely due to biological differences between the two. And so you might see the exposure effect among males and then a different exposure effect among females. So when evaluating the validity of a study, it's really important to take into account the study design as well as paying attention to the potential confounders that are in it. So in the case of causal analysis, I just want to highlight this because causal analysis, it's very important. Adjusting for confounding is absolutely critical. So here, researchers are trying to make some claim about what causes an outcome. And in order to make this claim, all confounders need to be accounted for. So that means there can be no unmeasured confounders out there in order to be able to accurately estimate that effect. And so the best way to deal with this is to conduct a randomized controlled trial, since the potential for unmeasured confounding is removed due to that random treatment assignment. But in the case of observational studies, there are advanced statistical techniques that can be implemented. For example, you can incorporate things like propensity scores or perform sensitivity analyses to quantify how an unmeasured confounder could influence that result. And so we're not going to talk about those kind of more advanced techniques in this course just because we're limited on time, but we've included some literature on them in the course notes in case you want to dive into that further. So returning to that prediction analysis, now instead of measuring the association between some exposure and outcome, or fitting a multivariable model with an exposure and measured confounders, now we're interested in predicting an outcome using a set of predictors. And so this looks a little bit different, but we're going to get into the specifics of prediction models and the classification methods and classification evaluation settings. Okay, so for the following sections, we're going to be discussing 3 types of statistical models. Statistical models that you fit when you have a linear or continuous outcome. Statistical models that you fit when you have a binary outcome. So this means a categorical outcome with just 2 levels. And statistical models that you fit when you have a time to event outcome. And so each of these models take on the following forms. So f of the outcome here, it's some function of the outcome y, and the effective interest is some transformation of the coefficient associated with the exposure. And so we're going to be talking about this in specifics for these different types of models in the following sections.